So my talk is on Rust. So Rust is marketed as sort of this systems programming language. It's got zero cost abstractions. It's got no runtime, this kind of thing. But I don't see it used as much for language development. So C has kind of proliferated this area, but I don't see a lot of uptake with Rust. And I would have thought that that would flourish in that area. So this talk is sort of an exploration of using Rust to do language implementation, in this case a simple Lisp, and also using Rust as a compilation target. So this compiler is written in Rust, and it outputs Rust, and the compiler will then take that and compile that into a native executable. So just a little background on me. I come from sort of an ML Lisp background. So I'm a programming language fanatic. I've used hundreds of different programming languages over the years, but I've never actually designed or implemented one myself. Actually, I take it back. I implemented a Lisp in Lisp, and that's cheating, and that doesn't count. And I also have very little low-level knowledge. So, I mean, I can't really speak intelligently about the difference between x64 and ARM, or undefined behavior in C, or all of those other gotchas that you have to sort of overcome in order to do any kind of low-level development. And most of my experience has been mostly in garbage-collected business apps. But that low-level stuff is really interesting to me. It was just really intimidating until sort of Rust came along. And I like the fact that it has a lot of ML influence. The pattern matching is very much derived from ML. In fact, it goes beyond ML into racket macros, actually. Not racket macros, but pattern matching, which is pretty cool. And it also has this emphasis on immutability. More to the point, it has an emphasis on managed mutability, which is the other side of the same coin, which is, I think, a nicer way of saying it. And actually, that bullet point about easy to learn, that's total BS, I think. It's not, it's, when I wrote that, I had something in mind. It's not easy to learn. Rust is a difficult language to learn. But when I wrote that, what I had in mind was the fact that a lot of the type system vocabulary, a lot of the things that Rust brings to the table, borrow checkers, traits, things like that, have a shared vocabulary with languages that I understand, like Scala and Haskell. So knowing that vocabulary from that side of things allowed me to onboard a little more smoothly onto Rust. So that's what I meant when I wrote easy, but it is not easy, so please ignore that. And it also has a very mature metaprogramming model, which I didn't expect. Right down to hygienic macros and more. And we'll look more into that in a second. In fact, in a lot of ways, it's better than Lisp's. But just a word to the wise, when I first started learning Rust 6 weeks ago, by the way, the first few weeks were really frustrating because the thing looked like an ML, right? And I tried to make it an ML, but it wouldn't turn into an ML. And like after I just accepted the fact that it's an imperative programming language, and I just went hog wild with like for loops and while loops with mutable counters and things like that, Rust actually became a lot nicer of a language to work with. So it's got a lot of ML influence. It's got a neat type system, but at the end of the day, it's still an imperative language. So just word to the wise. So the Lisp that I'm going to implement is called klambda. It's a pretty Lisp-looking Lisp. That's a function that takes something and adds one to it. Adder. And it's also schemish in the sense that it's tail call optimized, so we have to deal with that. So here's a function that gets the length of a list by recursing down the list and just accumulating the number, right? So that's a very schemish way of doing things as opposed to like using a for loop or something like that. But one of the unique things about klambda is that it's curried by spec. So currying means that say you have a function that takes like n arguments. If you only give it a couple of arguments, then it holds onto that couple of arguments, and you can pass that around as a closure and give it the rest later. That's what curried means, and klambda mandates this. So in retrospect, this is the worst part about this implementation. The most challenging part about this implementation had to do with dealing with Rust and currying, because Rust and closures do not get along. Let me put it another way. Low-level programming and closures do not get along because there's a lot of stuff that's in scope, and all of that stuff has to be managed by you now since there's no garbage collector, or by the borrow checker yelling at you and you doing what the borrow checker says. Also, it's tiny. It's only a couple of pages. And the nice thing is, yes, it has a spec, which means that there's other implementations of it. And I can test my Rust implementation against sort of like a, I don't know, a Ruby implementation. If they give me the same thing, then, there's a chance that what I did was right. So, parsing k-lambda. So when you parse k-lambda, you can stick the parse into some of these token types. Some of them are fairly normal for a Lisp. You have a symbol, which is a string. You have a number, which is an integer or float, or just a plain old string. A console, which is all of those in a vector, right? And this last thing called recur, which is a marker for tail call recursion, which we need later to optimize tail calls. So when I first started doing parsing, I decided to use nom. And why did I decide to use nom? Because I Googled how to parse things in Rust, and nom came up on top, and it seemed to have high GitHub numbers. And also, I looked at the API, and some of the and a lot of the function names were like things that I'm used to, like many 0 and many 1 and take until, and like all of these things that I'm used to in like parser combinator libraries in like Haskell or Scala or whatever. So I was like, okay, I can get in on this. This is fine. And as I got in on it, I realized that all of these parsers, combinators, were just macros within macros within macros within macros. So my first introduction to Rust was that, writing macros, which I don't recommend as an introduction to Rust. So here is a macro called named that generates a function called klstring that outputs something of type token. So it's going to take a string and marshal it into a token. So it uses a sub-macro called chain, which has further sub-macros inside of it. So chain takes a character parser macro, parses a single quote, parses things inside of that string, and then parses the end quote over there, and then marshals all of that into a string. The innards is another piece of magic that uses this like macro called escape to magically escape all of these like slashes and things like that. So there's a lot of just magic happening here. And my first couple of days when I was writing a few parsers, I was like, I don't really know if I want to continue with this library. Like, if it's going to make this much use of macros, and I don't really know Rust as it is, and now I have macros outputting piles of Rust, like, how am I ever going to like get anything done, right? But as it turns out, Rust macro debugging is really nice, even compared to Lisps. So there I've screwed up the KL string macro, and for a character, instead of a character, I've given it the string hello. And the type checker actually tells me that the error is in the macro, not in some like generated code, right? And that's something that I'm used to from like dealing with Lisps and things like that. Is like, not that Lisp has a type checker, but like if there's ever like a runtime error, it's pointing to like the thing that's the generated pile of code, which is really hard to debug. And this, by the way, makes macros totally practical for like everyday Rust development. If you have some boilerplate, just boilerplate it away in a macro. You're not accruing that much technical debt as you would with other languages. So I just wanted to throw that. That's just a shout out to Rust developers for doing this right, in my opinion. So parsing a symbol is only slightly more complicated. It uses that chain parser again. It parses one of a number of characters, like A through Z or something like that. And then the remainder, which is one or more of digits or characters. That's what many 0 does, and that's what alt does. Alt alternates between the two parsers. Again, the names, if you're not familiar with them, are chosen from parser combinator libraries written in Haskell or Scala. So again, there was this sort of like name consonants that I was able to like take advantage of when doing all this. And the last block over here just grabs all that stuff as a vector, joins the vector together, and marshals that into a symbol. So parsing an S expression is not that much different. So an S expression is just a thing within the parens, right? It's like the function and the arguments that go after it. So when you parse an S expression, you again use chain, parse in open parentheses, and this combinator called many 0 until. The reason I'm showing you this is not because it's complicated, but because this is the parser that pulled the veil back on this illusion of sort of functional programming parser combinator things, because I had to write that parser because it didn't exist as I wanted to in the NOM API. And I had to write a macro. And once you write that macro, there's no looking back and thinking that Rust is a functional programming language because it looks kind of like that. So that's a little terrifying if you've never seen something like that before. But if you look at it, look a little further, it's actually not too bad. So macro rules is the thing that generates a macro, so I have many 0 until, and macro arguments are passed in and pattern matched. So it's saying given some input expression, and a stop macro, which is sort of stop when you see like the end parentheses, and the sub macro, which is like do this to keep going. The rest of it is just standard looking Rust code with like those things spliced in different places. And it's just that easy to write a macro. Like you don't have to like know a whole different language, you have to know a little bit more syntax, but not a whole lot more. So now that we've parsed our Lisp, we are marshalling that into the sort of internal representation of this Lisp. So we have tokens, and this is how they look once the tokens are turned into something that can actually be interpreted and run. So we have an element, a lot of these are the same, symbol, number, string, a console, but what I want to concentrate on is this closure token right here. Because like I said, K lambda is curried. So we lean heavily on closures for just about everything. And like I said, that makes the implementation quite a bit more complex than it could have been if it wasn't curried correctly. And also this recur thing, which we need for tail call optimization later on. So here's the closure. So by the way, everything in all of our Lisp data types are reference counted because there are no immutable data types in our Lisp. So basically, once you're done with them, you can just drop them. I don't need to worry too much about garbage collection, which is quite nice. So the KL closure has 3 variants. Feed me. Feed me means I'm a function, I'm accepting another argument, and I'm going to hand you back another closure. So this models the whole, I have more arguments coming, I'm not done yet. Thunk, which is a special case because a lot of Lisp forms are special forms that don't follow like applicative order evaluation. So for instance, if, so in a standard Lisp form, when you pass something into a function, you evaluate the argument and you pass it in. But you can't do that for an if, right? So if you can't evaluate the if branch and the else branch before you pass it into an if, otherwise you'll have problems. You have to wait until the predicate is either true or false. So for that, we use thunks. And finally, we have done. That means I'm done, here's the final value, which is either a something, or nothing, or an error. So a case where it could be nothing is if you're writing something to standard out, or something like that. So here's us using that abstraction to write a primitive Lisp function. So our Lisp needs a bunch of primitive functions in order to bootstrap itself. So intern is a function that takes a string and turns it into a symbol. So intern is a function that's outputting a closure, right? So it is using feed me, which means I'm expecting 1 or more arguments. And inside of that feed me, RC new creates a new reference counted cell. Inside of that, there's a closure that accepts a string. And inside of that, you're destructuring that string, extracting it, and putting it into a symbol. There's a whole lot of accidental complexity here, unfortunately. So in essence, all this function does is take a string and stick it into a symbol. All of this does that, unfortunately. So where this makes more sense is if you have a function with more than 1 argument. And that's what this is. So pause is a function that, given a string and a number, just hands you back a character at that index, right? So same as before, we start with a feed me, meaning we're accepting more arguments. And we have a reference counted closure that takes a string. But inside of that, we have another feed me because we're accepting 2 arguments. But that closure requires a move keyword in front of it, right there. Why does it require a move? Because this is what is telling the Rust borrow checker that I'm going to be capturing something inside of my environment. And then you have to explicitly capture that thing inside of your environment. So that's where I'm going let string equals string.clone. That means I'm cloning the string from like the outer function. By the way, cloning here doesn't mean I'm copying the entire string because they're all reference counted. All that means is that I'm bumping up the reference. That's all that means. So it's a cheap operation. So, but you still have to do it. You have to manage these things yourself. And then you're destructuring the string, and then you're pulling that character out of that string. So here's an example of using the AND. So AND here is another Lisp special form because it needs to take arguments that are unevaluated. So here we're using thunks to do that. So it needs to be unevaluated because if the first thing is false, then the whole AND thing like short circuits and hands you back false. It should not like evaluate the second argument. So I've deleted all of that feed me and like reference counting stuff. And so it takes a thunk and a b thunk, moves the a thunk into the b thunk closure using a thunk.clone, forces that thunk, which is just a simple function that I haven't shown you, which gives that thunk an empty set of parentheses and gets back an element, and then pattern matches on what you just forced. If that thing is false, no, wait. If that thing is false, it's just false. If it's true, then force the second thing. So this is an example of using thunks that we've seen before. And then everything goes into this global mutable table. Rust doesn't really like you making global mutable variables, so it makes the syntax kind of hard to do it, but you can do it this way. So thread local is a macro that allows you to declare something in a static lifetime. A static lifetime means it's available for the rest of this program. It'll never be dropped. And a variable called function underscore table that has a ref cell, and a ref cell is something that allows you to have interior mutability. That means that a thing inside of a ref cell can be mutated over time, right? So inside of that ref cell, we have a hash map of a string going to a closure. So what that is just a list of all of our functions that we have. So in order to bootstrap our system, we fill in the function table, right? And we borrow the function table immutably using this like with construct. And then we insert position, insert and insert a whole bunch of other things that we need to sort of bootstrap this Lisp. You know, cons, tail, head, all of this stuff. And then when we invoke this in Lisp code, it just goes to look it up. It looks it up in that function table, this time not borrowing it mutably, but just borrowing it, right? And then it gets the function, and it either returns the function or it doesn't, if it doesn't find it. So bottom line, a function, an expression like cons1 nil, which is just a single element list, right, outputs this Rust code right here. So like the compiler will output this Rust code where it says function apply, and function apply is a wrapper around looking up something in that function table and you know, applying some arguments to it. So go get me a function, a closure matching cons, and then give it a reference counted number 1 and a reference counted empty cons. And then hand me back a new cell, hand me back a new cons with one thing in it. And if that's okay, go ahead and clone it. If that's bad, go ahead and propagate that error. Things unfortunately get a lot more complicated when we're looking at lets and lambdas. So in K-lambda, a let can always be rewritten as a lambda. So here we're assigning x to 1, and then we're adding x and x, doubling x, right? So that translates to a lambda where a lambda that takes an argument x and adds it to itself, and then is applied to 1, right? Those two can always be rewritten that way. But this is the outputted code. It is unfortunately complex, and I don't know of a way around it. So here I have a function called apply lambda that takes something that looks a lot like what we saw before in the primitive functions. It's a feed me data type, inside of which we have a reference counted closure that uses the move keyword because it might capture something in an outer function. And then it makes a wholesale copy of whatever is inside of that reference counted cell. And the reason we have to do that will become clear in a second. It's not a great reason, it's an unsatisfying reason, but the reason we have to do that will become clear. So it makes a copy of that, then passes that copy to the plus, where we're adding the two things together, and then way down at the bottom, it passes in that 1. So why do we have to do that copy? It seems wasteful to do a wholesale copy of like a whole string or something like that. And the reason is the Rust borrow checker. So let's get rid of some complexity and look at the complexity we want to look at. So here's where we're applying the lambda. and we move and we move like the environment into that X closure. And the reason we're doing that is because when we want to copy it, right? When we move X into a sub closure, that X is now gone away. So for instance, here's a let, we assign X to 2. And then we do X times X, and then throw away the computation and just return X. So here, X is being used in 2 different places. It's being used where you multiply it with itself, and it's also just being returned. So we need X to be accessible in 2 places. And that's where the complexity comes in. So here we have all of that accidental complexity, and here we have the accidental complexity we want to look at. So what that decompiles to is a closure that copies X and then moves X into Y, because that's where X gets doubled. And the problem is that once X moves into Y, it's no longer available. Like the Rust bar checker says, once you move that into this closure, once this closure goes out of scope, I'm going to drop it. So any further uses of X are invalid at that point. So that's why I have to do a wholesale copy, and then in order just to reuse it down here. And a whole portion of the complexity of writing this implementation had to do with making sure things were copied correctly. And in fact, it does a lot of copying that it doesn't need to do, because it doesn't do a whole lot of static analysis. This is a fairly naive implementation. So, on to tail calls. So, tail calls are, so here we have a function length where there's a tail call down in the second predicate action pair. So length is, so what we have is a path down to the tail call. So what we maintain is a number. So 3, 2, 1, so count down to the third element starting at 0, defun, length, the args list, and the con, that's 3. 2 is the second predicate action pair, and 1 is the length. So that's how we detect it. We walk down the AST and find the recurrence. This is what that AST looks like in Rust code, in Rust data types. It's a lot more verbose, but the underlying structure is still the same. So there's the tail call way at the end. And when we go ahead and mark this tail call, we use that recur data type that we defined way in the beginning. So we get to the tail call, we mark it recur down the 4th line over there, but keep the arguments, right? So now that is a marker telling me that at that point in the code, there is a tail call that needs to be optimized. And we have a similar data type on the internal side, on the internal data type side. That's just also called recur, but instead of a list of tokens, it keeps a list of elements. And now we add the trampoline to the function. So what happens is that we have the standard closure that we saw before. It takes an accumulator. An interior closure takes the list. But now we have a trampoline that takes the accumulator and the list and generates all of the giant like Rust code inside of that trampoline. But at the point where it would like call itself, it returns this recur data type. And it applies all of the functions, like if you're going to add 1 to a number or something, it happens right there, sticks it all back into the recur data type, and then returns it. Okay. Now we have, underneath the trampoline, we have a while loop. So we have a flag that signals when something is done or not, like are we done recurring or not. And then we have an initial set of arguments, which is the set of arguments passed in. And in the while loop, we just keep passing those arguments to the trampoline until it is not a recur data type anymore, because that point means it's done. And then we unwrap it. And that's how we get tail calls. It's not the most efficient way of doing it, but it works. Any questions so far? Okay, yeah. So a trampoline is a function it's called a trampoline because that's what it's called in like programming language theory and stuff like that. It's not really a great name, but it's a function that instead of a tail call will just return the arguments passed in so that you can keep passing them in again and again, because if you didn't do that, you would blow out your stack frames. And Rust doesn't do tail call optimization, which is not great. Apparently LLVM does some tail call optimization, but I was never able to get it to work with Rust. So like everything that I tried like blew out the Rust stack, unfortunately. Yeah.
I think the borrowing model in Rust is incompatible with tail call optimization. I might be wrong about that, but
It's possible. I don't know the answer to that. Yeah.
how did you first identify that you needed to apply the return tag to it? I missed that one spot where you basically identified it as a token and then you knew to handle it.
Oh, I didn't show you that piece of code because it simply walks this const tree. So it walks this const tree and looks for a symbol. It looks for a list where the head of the list is the symbol, which is the name of the function that I'm in right now. And then it just marks it. Yeah. So that's how tail calls are optimized. It is an unfortunately it's kind of a hacky way of doing it if you think about it, but it does work. So to run some benchmarks, this is like either the best or the worst part of this presentation, unfortunately. So here's a benchmark where all I'm doing is building a list of cons. I'm building a list. So I'm building a list of 100,000 elements, starting from 1 to 100,000. Actually, 0 to 100,000, 9,900, something like that, whatever it is. In any case, SBCL, which is a heavily optimized list implementation, does it sub-second. It almost takes longer to print it than it does to like actually do the computation. It starts off, when you start an SBCL REPL, it starts off at 23 megabytes of memory. It just grabs that right off the bat. And when you do this computation, it jumps to 50 megabytes and just sits there and just sits there and just sits there forever until you actually do something. So what SBCL does is like it waits until you hit a certain threshold before it runs a garbage collection cycle. So that's why it's using all that memory. Lua, and by the way, I used Lua in this benchmark, might be kind of surprising because it's one of the few scripting languages that is also tail call optimized. So we're comparing apples to apples here to some degree, not completely, but yeah. Again, runtime was sub-second. Memory initially was 2 megabytes. You go into the Lua REPL, you eat up 2 megabytes right off the bat. It jumps to 14 megabytes, and it holds there. Again, same thing. It's waiting for a garbage collection cycle to come along. Guile, which is a scheme implementation, its runtime it takes about 1.5 seconds, 15 megabytes initially, up to 18, and holds. My awesome Lisp code takes 7 minutes to do the same thing. Yeah. So I don't know whether to be proud of that, but here's the thing. It used the least memory of all of them. It holds steady at 5.5, and I know it holds steady at 5.5 megabytes because it takes 7 minutes, and I can actually watch my task manager. I'm like, yep, still 5, still 5. So up to 6, nope, back down to 5. Woo! Yeah, one of these things. All the others I couldn't observe. So like, I'm kind of proud of that. And I think that, and here's the takeaway. I definitely need to do more static analysis, right, on the Lisp code. I'm copying things where they don't need to be copied. I'm cloning things where they don't need to be cloned. Reference counting, when you're doing a clone, it doesn't have much of a runtime cost, but it does have a runtime cost, so I'm possibly doing that. Currying is complex. All of my functions are curried, which means they get arguments one by one, whether they need to be curried or not. And a vast majority of code, all function calls are saturated. You give the function everything it needs for the most part. You don't usually carry around closures. So every function call is paying the cost of currying that is used by a few. So the way around this, I guess, is just to sort of keep two versions of the function floating around, one that takes all of the arguments and one that takes 1 or 2 of the arguments at a time. So there's plenty of low-hanging fruit. And also, please bear in mind, I started Rust 6 weeks ago. So my Rust, I'm not writing the best Rust code here. The code generation. So yes, Rust has this like quasi package that like allows you to quasi quote Rust code and output that, and that's pretty nice. But I found the API too complex, so all of the code generation is done by strings. Like it's great. It's just it's just string handling, straight up, you know, like so it's bad. And also, generating Rust code was sort of something that I hadn't seen too often before. So this is where you generate a very strongly typed language as sort of the format of like a weaker type language like Lisp. And what I found was that it was very hard to do. A, because I don't know Rust very well, and therefore generating Rust is, you know, an order of magnitude more complexity. And B, because when you generate something that's strongly typed, the type checker catches a lot of the errors ahead of time. So I think that that makes it worth it for a certain subset of applications. Optimizing Rust to make the generated Rust on par with, you know, like the SBCL implementation or all of this stuff is probably going to take a lot more work. But I think in the end that something like that would be worth it. In any case, that's all I had, and I'll take any questions. Yeah. It spends its time in a lot of places. So there's no, if you're asking if there's like one hotspot, I couldn't find one. So it spends its time copying things that shouldn't be copied. It spends its time currying things that shouldn't be curried. So basically, like, yeah, there's plenty of low-hanging fruit there. It's a very naive implementation at this point. And plus, you know, I don't save things off to like an intermediate. So like if I'm applying a whole nested list of things, I don't like go, okay, let A equals this thing, let B equals this thing, and then apply A, B, C, and D. Here, it's all done in line. So I don't know how the Rust compiler deals with things like that. But yeah, it was kind of fun trying to find out. Yeah.
So did you need to call rustc explicitly on the output of your parser, or is there some library that you can compile and run within Rust?
So there is a file in Rust projects called build.rs, and what that does is you can arbitrarily output Rust code into your project, and when you do a cargo build, it will just build all that Rust code for you. There's a way to do that, but I haven't done that here yet. This is just sort of a initial implementation. Yeah.
You said you started learning Rust 6 weeks ago. How much time did you spend a week to get this far?
20 hours. Yeah. Yeah.
So I just want to make sure I heard something.
Yeah.
Were you saying that you like Rust macros better than Lisp macros? I know you said that, but I want to hear you say it again. Why?
Rust macro debugging is nicer than Lisp macro debugging, at least as far as I can tell. And Rust uses scopes to like enforce hygienic macros, which is a nice thing to have. And a lot of Lisps don't have that. Schemes do, but a lot of Lisps don't. So that's kind of a nice thing too. And also, Rust actually, to a small degree, type checks your macros ahead of time. So if you if you say you're going to pass in an identifier and you pass in an expression, it'll catch that at that time, and you don't have to like deal with it.
Is it as powerful as Lisp macros?
The short answer is no. Like there's things that Lisp macros let you do that Rust macros don't let you do. So for instance, a Rust macro, you can pass in a bunch of things with a star at the end of it. So if I go like a star in a Rust macro, that means that I have a whole bunch of things coming. But in a Lisp macro, I could take that as a list and like, you know, do whatever I want with it, like, you know, get the length of the list or whatever. But in Rust, I can't do that. But you can do that if you're writing a compiler plugin, which is sort of, I thought, out of scope a little bit, but not completely out of scope for the project in general. Yeah?
Not really a question, just a statement that if you're familiar with scheme macros by example, that's more or less, or syntax rules,
Okay.
that's what Rust implements.
Oh, okay. Oh, cool. Well, sorry, I'm not that familiar with syntax rules.
I'm more answering the
Okay, cool. All right. So he was saying that scheme syntax rules pretty much implement what Rust does. Nope, not optimized. Sorry, just if you got it's got to be a tail call. It's got to have no context, and it's got to have everything it needs to just be done after the tail call is done. Yep. Would be nice. Okay, thank you.